All right. Well, thank you guys for inviting me to talk. This is um, kind of a project that was built out of my connections with Troy. So Dr. Roblee kind of gave me this idea a couple of years ago of looking at harmonious labelings when I had a couple of students from my combinatorics and graph theory class come and ask me if I would do a undergraduate research project with them on graph theory, which I'm not really a graph theorist by trade. My main area is commutative algebra, but in my work I do deal with some graph theory and combinatorics, and this seemed like a neat problem, so we kind of took it on. So I'm going to give you guys a little bit of introduction, just in case you're not familiar with harmonious labelings and kind of how we got started on the path that we did get started on. And then I'm not going to go into any like really detailed proofs because the turns out that the organization of the notation and the stuff that we had to do to actually prove a lot of these results was very technical, confusing to look at. It was just a lot to keep track of. So I think for a talk that might be a little overwhelming. So I'm going to focus mostly on the background, some of the basic setup, how we use some abstract algebra. I'm in here a little bit of group theory to work with these graphs and find these harmonious labelings. So I'm going to just assume up here we're going to be dealing with standard graph notation. So we've got a graph G with a vertex set V and an edge set E. We're going to be dealing with only simple graphs. And just for the sake of our harmonious definition, we'll say that the vertex set has n vertices and the edge set has m edges. So we define a harmonious labeling to be this injective function from the vertex set to z mod m. So z mod the number of edges that we have in our graph. Okay, so where for each edge that we have in our edge set with adjacent vertices u and v in our vertex set, then we can label that edge E with the sum of these vertex labels here mod the number of edges. So meaning basically if I have a vertex labeled 5 next to a vertex labeled 3 and 5 plus 3 is equal to 8, when you go mod the number of edges, then we label that edge 8. Okay, and so all these vertices have to be unique in Z mod M. So after we add up the sums of all adjacent vertices to label our edges, then we have to get a unique set of labels for all those edges. And so any graph with a harmonious labeling is said to be harmonious. And for this particular talk, pretty much most of the graphs, other than one example, are going to either consist of or contain trees. And so since trees have one more vertex than we do edges, then we're going to allow for, or we're going to allow basically for one of those vertice labels to be repeated. So I'll kind of show you that in an example here. So just these are a couple of known harmonious graphs. So odd cycles are known to be harmonious. So this is just C5 over here. Now this is not a tree. This is the only example I have that doesn't contain a tree. But basically what you do here is we have 5 edges. And so that means we're working in Z mod 5. So I can just, on these cycles, you can pretty much just label them in order. So I just choose a label for 0 for one vertex, and then I go 1, 2, 3, 4 all the way around. And then we add up our vertices mod 5 to get our edge label. So of course 0 plus 1 is 1, 1 plus 2 is 3, 2 plus 3 is 5, so mod 5 that would be 0, and then 4 plus 3 is 7, but go mod 5 you get 2, and then 4 plus 0 is 4. So that's a harmonious labeling because all of those edge labels that I get there are exactly the elements in Z mod 5. So you get all of your elements back from Z mod 5 and they're unique. Okay, and then down here, this is just another example. Now this one is a tree, it's a path, right? So this is P5. So I have my vertex labels here where I need to repeat one of them since it's a tree, because I only have 4 edges here. So this means I'm working here in Z mod 4. And so I'm doing everything mod 4, but I just chose to label 0, 1, 3, and then 0 over here to get what I want, and then 2 on the end, and that gives me a unique set of labels. There's different ways you can label some of these paths depending on the length of the path, but this was just kind of a simple example to give you an idea what was going on. Okay, so that's just some setup examples. Now, this is what I call my motivating example. So this graph up here, capital T sub ST plus 1, we call that a star-like tree consisting of T paths of size S or length S, so PS, joined at the endpoints of each path by a central vertex called the root. So we have this red vertex here, that's what we call our root. And then we just take our paths, these are all paths of length 5, so each of these is a P5. And then we join one of the end vertices of each of those paths to that central vertex. And we have exactly 4 or T of those paths of length 5. So you can see in this example, this is, I've got S is 5 here, so paths of length 5, and then I have 4 of them, so this is T of 5, 4 plus 1. And we have exactly 5 times 4, or 20 edges there. So if we were to try and harmoniously label this graph, we would be working in Z mod 20 here for this particular example. Okay, so now this is kind of how we got motivated on this. Dr. Roblee, he and Abueida had a paper where they showed, one of the things that they showed in that paper is that the disjoint union of a cycle of length S with the star-like tree T sub ST plus 1 is harmonious when we assume that S is bigger than or equal to 3 and odd, and T is bigger than or equal to 2 and even. So an example, or well, I'll give you an example in a minute. So I'm going to kind of show you why I was interested in this particular problem, because they proved this result using a little bit of group theory and dealing actually with properties of cosets within Z mod, whatever we're working in here. So what we have here is if we take a cycle of length S, that's going to have S edges, and then T of ST plus 1 is going to have S times T edges. So that's going to give us exactly S times T plus 1 total edges that we're working with. So that means we're working in Z mod S times T plus 1. And by assumption, remember, we assume that S is odd, and T was even, which is going to mean that T plus 1 is odd. So these are both odd, so that product we get up there is going to be odd as well. And that's kind of important in using all this group theory, is you want to be working in Z mod something that's odd, essentially, to make things work right. So kind of what we do here, how we introduce our cosets to help us label this graph, is we let H be this subgroup generated by T plus 1. And so we know that H is going to have exactly S elements in it. If you actually write out the elements in H, there's going to be S things in there. And there's going to actually be T plus 1 distinct cosets of H in Z mod S times T plus 1. So we can write those down. You're going to have 0 plus H, which is just H. I just write that there to indicate that that's the 0th coset. And then you got 1 plus H, 2 plus H, and so on, all the way up to T plus H, right? So if you count that, start counting at 0 all the way to T, that's T plus 1 cosets. And so each of those contain exactly S distinct elements. So doing it this way, in each coset, we get sets of distinct elements throughout. And so kind of the idea for harmoniously labeling this graph is we start by labeling our cycle. So we label the cycle with elements from the 0 coset, 0 plus h, or just h, where you just pick a starting point on there and you just label them in order, kind of like we did that example with C5 when we labeled the cycle earlier. And then when we start labeling the starlike tree, we choose to label the root with 0. Now that's our repeated vertex because 0 is also going to live in the 0 coset. So that's our repeated vertex of 0, which we are allowing for one repeated vertex since we're working with a tree here. And then we're going to label the distinct paths of TST plus 1 with the ordered elements of the cosets 1 plus h, 2 plus h, ... k plus h, that's a middle one. I'll explain why I put that one there in a second, all the way to t plus h. So we just kind of do that around, but we do it in a certain order. So we do this so that the order of the coset elements is smallest to largest if our coset location k is odd, and largest to smallest in terms of the ordering of these values if our coset location k is even, and that's beginning at the root and moving away from it. And we could reverse that order too, and the labeling would still work. We just have to do that to make sure we return some missing elements when we start finding our edge labels. Okay, so let's just do this for an example here. So this is C5 union T5 4 plus 1. So that means we're going to have 5 times 4 plus 1, or 25 edges. And so we're working in Z mod 25. So if we compute our subgroup here, or H, that's going to be H is equal to, remember, the subgroup generated by T plus 1, which is going to be 5 in this case, 4 plus 1. And so we get these elements 0, 5, 10, 15, 20, right? So that's our 0 coset. And we have exactly S elements in there, which S is also 5. And then we can compute our first coset element, second coset, third, and fourth. And you can see how we do this. You essentially just add 1 to each of the elements in the previous coset to get the elements in the next coset. So this accounts for all of our distinct elements in Z mod 25. And then we go down here and we just start labeling the cycle first with elements from the 0 coset. So I just label around in this fashion where I start with 0, 5, 10, 15, 20. And you can see that's going to give me unique edge labels back from the 0 coset. So when I add elements from the 0 coset, I just get elements back in the 0 coset. And then moving down to the tree here, so I'm going to choose this edge label here. So these are going to be my vertex labels from 1 plus h, so the first coset. And I order from smallest to largest, moving away from the root, which I've labeled 0 there, you can see. So 1, 6, 11, 16, 21. And what happens is, if you check this, the edge labels, other than this 1 here at the beginning, the edge labels here I get back, these are all elements in the second coset. So basically, when I add 2 elements from the first coset, I'm going to get back an element from the second coset. And so that's almost all of our vertex labels from the second coset. The only one we're missing is the 22 up there. So I need to recover that, which is why I start, when I go down here and I start labeling from 2 plus h on the next branch, I start with the biggest element from that second coset and attach that to the root with a 0 label so I can recover the 21 that I was missing from my labeling from 1 plus h. And then when we add up all of our elements from 2 plus h in there, so when I add elements in 2 plus h, I'm going to get stuff back in 4 plus h. So if you look at all these edge labels here, these are all in 4 plus h, but I'm still missing some. So for example, you can see I'm missing 24 there, but I have everything else. So again, that's why I kind of go over here with my 4 cosets. This is my 4 coset labeling, 4 plus h, and I started there with 24 and went largest to smallest, just like I did with the 2 coset. And so adding stuff up in the 4 coset, I get stuff, you can see those are going to be in the 3 coset. And that's the 3 plus H coset. And the reason for that is if I do 4 plus 4, remember, I'm working with my cosets, or my H is being generated by 5. So when I add stuff in there, I'm thinking of going mod 5 on the cosets when I'm adding these up. So if I add something from the 4 plus H coset, well, 4 plus 4 is 8, mod 5, you get 3. So when I go back and when I add 2 things up, I get something back in coset number 3. And then you can see I have everything there from coset 3 on those edge labels, except I'm missing the 3. So that's why when I start labeling from the 3 plus H coset down on this other branch, I start with 3. And then when I do stuff in the 3 coset, so 3 plus 3 is 6, go mod 5, you get stuff back in the 1 coset. So those edge labels are going to be back in coset number 1. So I drew all over that slide, and now it looks like a mess, but this is kind of the idea behind the procedure that they used when labeling this union of this cycle and this star-like tree. So this was a really interesting process to me, because I thought it was really cool how they were using the properties of these cosets to show that you get these unique labels. And then the only real technicality they had is reversing the ordering, moving away from the root, depending on whether or not you were in an even coset versus an odd coset. And so that's kind of what we started looking at, and we were thinking, how could we improve on this? Well, one of the first things that we saw immediately is we kind of saw an immediate corollary to their theorem. So if we take the graph, just the star-like tree by itself, TST plus 1, with S and T bigger than or equal to 3, and both odd, then that's harmonious. And this is actually an immediate consequence of the previous theorem, because what we can do is we can break apart the cycle, CS, between the labels 0 and T plus 1, and then just connect the label T plus 1 to the root of TST plus 1. And when we break apart CS, we get a path. So if you go back over here and you think about, so I'm going to erase a little bit, my cycle up here, if I just basically break this cycle right here at this edge between 0 and 5, and then I connect the 5 to the root down here, then I maintain my 5 edge label, and I maintain all the rest of my labels on that cycle, but I get another star-like tree instead of a disjoint union. So that basically looks like this. So you can see I broke apart this cycle at 0 and 5 here, and I connected the 5 to this root. And so this is T of 5, 5 plus 1, which is, it's also a harmonious labeling. So this was kind of an immediate thing that we saw based on what they did. I mean, this is not really any significant result or anything, but we thought it was kind of cool. And so we thought, okay, well, where could we go from there? And so I had this great idea, which turned out to be, in some senses, a terrible idea. I just saw a typo there. It's supposed to be cosets. Sorry about that. We were curious as if we couldn't extend this idea of basically using the cosets to harmoniously label a graph, where we also included the use of subcosets of our subgroup H. So this whole setup here kind of is what developed this snowflake graph. So just to preface this, I know I said this initially, but this is all joint work with 2 of my undergraduate students, Holly Landers and Walker Maddox, who they've since graduated, but they found a pretty neat little result, which I'll kind of show you their results a little bit later on as an example. And they presented at the Troy Math Fest in 2019, which I believe was the last time you guys had it, since it was canceled last year. So what is the snowflake graph? Well, basically what we did is we took our star-like tree, TST plus 1, and we just added an extra layer of depth to it, if you will. So we're going to do this in such a way. Now I'm going to define this kind of in such a way, the way I want it to define to prove my results. I should say that I don't have to require these to S, T, and R to be odd to really define the snowflake graph. I mean, some of them, so the one thing that I do have to have being odd is this R, but S and T could potentially be even and you'd still get a snowflake graph, but I'll talk about more about that at the very end. So we want these to be bigger than or equal to 1 and all odd, but not all 1, because if they're all 1, then it's boring. You just have a point, which is no fun. So what the snowflake graph is, it's the graph formed by overlaying the central vertex of a path of length r on top of every vertex of this starlike tree, TST plus 1, except for the root. So except for that vertex that our paths are connected to. And so what we do is we call this the snowflake graph with T branches. Okay, so T in SF and our starlike tree, TST plus 1, are the same. And each of those branches still has length S, but then we have these sub branches of length R. So to give you guys a visual kind of picture of what it looks like, this is an example of the snowflake graph, SF3, 5, 5 plus 1. So what I've got here is I have 5 main branches coming out of my root, and each of those branches initially consists of a path of length 3. So that's my S. And then on each of those vertices on those paths of length 3, I've overlaid another path of length 5, which is, that comes from my R value. So you can kind of see why we called this the snowflake graph. I mean, it looks kind of like a snowflake. So we just, I mean, it wasn't really a clever name. It just seemed like a good thing to call it. But this is what we were trying to basically make a harmonious labeling of. And initially, when we looked at this, we thought, oh, this is maybe not going to be that bad. We kind of saw an immediate or a fairly immediate pattern that we thought might work. And we thought we had it. We were pretty sure we had the solution, but we ran into a weird little technicality that we hadn't expected. And so kind of most of what I'm going to talk about is, you know, how that technicality arose and how we kind of took care of it. So let's just start by some observations here. So first we observe that this snowflake graph, for example, just this one we looked at in the previous example, SF355 plus 1, it's going to have exactly 3 times 5 times 5 edges, which is 75 edges. So a lot of edges. So if we were going to harmoniously label this, we'd be working at Z mod 75. Now in general, if we're looking at a general snowflake graph, we're working in Z mod S times T times R if we wanted to harmoniously label this. So our initial thought, I'm going to give you kind of the initial setup, and we thought this was going to work, and it didn't really work, but it gave rise to something that did work. As we initially thought, well, let's let H be the subgroup generated by just T in Z mod STR. Then we know that there's exactly T distinct cosets of H in that group, so Z mod STR, and they each contain exactly S times R distinct elements. Now for our subcosets, we needed to define a subgroup, something that was a subgroup of H. So we define K to be R times T. So that's going to give us R distinct subcosets of K, each of which contain exactly S distinct elements for each coset of H. And I know what some of you might be thinking. I was like, good grief, this is already too complicated to kind of manage, especially in a general sense. And it was pretty terrible for a little while. We had to really think about how we could clean things up. But even still, we were only able to, I think, clean stuff up so much. There in the way that we proved a lot of our results required a lot of initial lemmas about how elements add up in the group theory sense before we even got to the the graph theory sense. So here's an example. I know this is like a big example, but I wanted to choose different values for T, R, and S to just, that way they don't match each other. So I'm going to let T equal 3, R equal 5, and S equal 7. So in that particular space, then I've listed, we would have, T times R times S would be 105. So we'd be working in Z mod 105. And so I'm basically written a table down there that's going to list the distinct cosets I plus H. So what we do is we would define our K. So our K, remember, this is going to be T times R times T. And then this H, this is generated by T. So that's going to give us 3 cosets for H, 0 plus H, 1 plus H, and 2 plus H. And then since my R is 5, I have 5 subcosets within each coset. So I just labeled those. You can think about this down here. This is the column for my subcosets. I've got my 0th subcoset, 1st, 2nd, 3rd, 4th, and I've written them out in each of my cosets there. So we've got 105 distinct elements listed in there between 0 and 104. And just to be clear about how these work, I mean, if you can see, since H is equal to the subgroup generated by 3, and K is the subgroup generated by 5 times 3, essentially, when I move from the 0th coset to the 1st coset, it's all of the elements in the previous coset basically multiplied by, or add 3 on, because that's how I'm increasing or multiplying things in K when I multiply by the generator of the T from H. So I can just calculate all my elements in the first subcoset in 0 plus H by taking the previous elements and adding 3, and then you go to the next one and you add 3, and so on. Okay, and then for the first coset, you do the same thing we did before. You just take all the previous coset elements and add 1 to each of them, and then same thing for 2. So this is essentially how we set this up or think about it. And I'm going to come back to this table a little later because we're going to kind of clearly define how we can write elements out in this set. Okay, so what was our plan here? How were we planning on labeling this snowflake graph? Well, we saw kind of something that seemed to work right away. So our initial thought was to label each branch with the elements from a single coset, such that we label the central vertex on each branch with the 0th subcoset elements in order. So basically what I mean is all of those central vertices that we overlaid the paths of length R on, we would put just the 0th subcoset elements on those central vertices. And then we'd have to do some sort of clever alternating order for the remaining sub-branch vertices. So we use the other subcosets within that particular coset to label the vertices on sub-branches based on their corresponding position from that central vertex of each sub-branch. So I know that sounds confusing, and it is, but it seemed like it might work, but we sort of ran into a little bit of a problem. So I want to kind of illustrate the problem that we ran into with an example. So I'm going to move out of my slideshow for just a second, and I'm going to pull up a smaller example. So this is kind of the smallest example. Can you guys see that graph?
Yes.
Okay.
Yes.
So this is kind of the smallest example that I could think of that would not be sort of trivial and not just a tree. So this is let me make that a little bigger. This is SF333 plus 1. So a little bit boring, but that means that we're working in Z mod 3 times 3 times 3, so 27. And if we were going to do this based on our setup, I'd let my H be the subgroup generated by 3, And then I let my K be the subgroup generated by 3 times 3, which is 9. So this would be just T times R times T. Okay? And so I just want to write down the elements, maybe in a table format, from each subcoset within each coset. I mean, it's not hard to do. There's only 27 of them. It's not too bad. So I've got my 0 plus H coset, my 1 plus H coset, and my 2 plus H coset. Okay, so I'm just going to try and make a table here. Hopefully this is all legible. And then here I've got my 0th subcoset, first subcoset, and second subcoset, kind of like that previous example. So in the 0th subcoset of 0 plus H, I've just got my multiples of 9. So I've got 0, 9, and 18, which if I did another multiple, that would obviously be 27, which would be 0. So I don't include that. And then for the first subcoset, I take all my elements from above and just add 3 to them. So 3, 12, 21, and then add 3 again, so 6, 15, and 24. So that accounts for all of my subcoset elements or all my elements in the 0 plus H coset, or just in H. And then for the remaining ones, I can just add 1 to all of the elements in the sets on the left. So I'll just have 1, 10, 19, and then 4, 13, 22, and then 7, 16, 25, and so on. So I'm going to keep doing this. Go ahead and write it out. So that's going to be 2, 11, and 20, and then 5, 14, 23, and then one more, 8, 17, and 26. So there's all of my elements in Zmod 27. Now let's kind of see if we can't label this a little bit. I'm going to pick a different color here. So we label the root, this red vertex in the middle. We'll label that 0. That was our setup. Make it a little bigger. And then I'm going to choose this first branch here to label my stuff from the 0 plus H coset in. So I'm going to do this in such a way where I use the subcoset, the 0th subcoset elements on the central vertices of this branch. So those are my central vertices of this branch. And I'm going to do it in a certain order. So the ordering I'm going to use is I'm going to start with the biggest element, which is 18 in the 0th subcoset, and I'm going to go down. So I'm going to go from biggest to smallest. So it'd be 18, 9, and 0. And then on these sub-branch points over here, I mean, there's a particular order that you have to choose to make things work in terms of where your elements need to sit to label if you've got longer paths sitting on here. But this one's pretty easy. I don't really have a choice here. I'm just going to choose to say use the second coset on one side and then the first subcoset on the other side. And you want to maintain the ordering, though, from biggest to smallest, just like we started with. So maybe I'll do up here, this is my second subcoset elements, 24, 15, and 6. And then down here, I'll do my first subcoset elements, so 21, 12, and 3. So everything's fine so far. I'm going to kind of keep going on down to this next branch. So I'll use my 1 plus H elements down here, but I'm going to switch the ordering out, kind of like they did when they were showing that the starlike tree union with CS had the harmonious labeling. They had to switch the order moving away from the root between odd and even cosets. We're doing kind of the same thing here. So I'll start with the smallest element, but I'm using 1 plus H, the 0 subcoset in 1 plus H for the central vertexes here. So I do 1 there, and then 10, and then 19. And then I kind of maintain that ordering, so where I'm going from smallest to largest for the other subcosets of 1 plus H. So like, for example, put 7, 16, 25, and then what was my other one? 4, 13, and 22. Now, before I go up here and I do my 2 plus H stuff, let's go ahead and compute some of these edge labelings here. So remember, working in Z mod 27, so if I label these, some of them are easy. Some of them you actually have to go mod. But you're going to get 18, 0, 9. And then let's see, this is going to be 12 because I got to do 18 plus 21, but then I have to go mod 27. And then the next one would be 21, 3, 6, 24, and 15. Now, if you inspect those elements there, you notice that all of those sums, all those things that I got back, it's actually all the elements in 0 plus h. Okay, I got everything back I wanted to get back from that set. And you know, when we add two elements in the 0th coset, you get stuff back in the 0th coset. Well, when I add stuff back in the add elements in the first coset, I'm going to get stuff in the second coset. So except for this first sum between 1 and 0 there, that's going to be the only thing that I don't get back, which we need to recover what we're going to miss from that one. But for the rest of them, 1 and 7 is 8, and then 5. Let's see, I get 11 there, and then 26, 23, and then I have to go mod on these last ones, so that's going to be 2, since it's 29, mod 27, and then, let's see, I get 17 and 14. So you can see, I mean, those are all elements, other than this one I have kind of at the top. Everything there is from the second coset, so 2 plus h, except I'm kind of missing one element. So let's see which element I'm missing. I've got 2, 11, so I'm missing 20. So 20 is the thing I'm missing from those edge labels. So it makes sense that when I go to this second coset over here and start labeling it, that I would start here at 20 so that I could recover that value. And that's initially what we thought was going to work for us. So maintaining the same pattern that I did before, I'd use the 0 subcoset on the central vertices here. So I go 20, 11, and 2. And then in the other ordering for the other ones, you just maintain the same ordering. So I could do 23. This is the first subcoset elements. 14, 5, and then 26, 17, and 8, right? And so when I add things up, I get 20. And then I get, let's see here, this would be 19, and then 16. And notice sums of stuff in the second coset element, second coset here are going to give me stuff back at the first coset, which I'm missing so far. And then, let's see, this is going to be 4, and then 25, and then 1, which you might be thinking, uh-oh, and you're right to think that, and then 13, and 7, and 10. So what we have here is we have a problem, right? I have this 1 popping up, which doesn't seem like it should be popping up there because that's a repeated label. So now I have a labeling that is almost harmonious, but it's not. I'm actually missing one of my first coset elements in there, and we couldn't initially figure out how to get it back. So this was really interesting. We were like, okay, well, why is this not working? We couldn't figure out initially why this labeling wasn't working out the way we thought, because it seemed like it was working the same way it should work based on the 0th subcoset branch and the 0th coset branch and the first coset branch. But in general, it wasn't working out right. So if you notice here what's happening, if I take maybe just a couple branches here and look. So let me highlight that better. So if you look at this outside branch over here, 22, 13, and 4, those are elements from 1 plus h, if you will, but in the first, let me not use that pen anymore, first subcoset. And when I add stuff in 1 plus h to, and the spine elements over here, the middle ones, those are in the 0th subcoset. So you would think if I add stuff in the 0th subcoset to the first subcoset, I get stuff back in the first subcoset of 2 plus h, which you do. You get 5, 23, and 14, which is in 2 plus h in the first position. Similarly, if I kind of look over here on this side, okay, so you notice that outside branch, that's the second subcoset of 1 plus h. So you'd think if I add 2 elements in there, you would get, so you're adding stuff from the, let me rewrite that. So second subcoset plus the 0th subcoset, because that's the central branch, which we're doing, in 1 plus h, would yield, you'd think it would yield elements in the second subcoset of 2 plus h. And if you look, 17, 26, and 8, that's exactly what you get. You get the second subcoset of 2 plus h. So all that works fine for those branches and even 0 plus h. The problem is when we start looking up over here on this branch. And so what I'm doing, say in this one, so the outside branch 5, 14, and 23, that's in the first subcoset of 2 plus h. So if I do the first subcoset plus the 0th subcoset of 2 plus h, based on what we saw previously, you might be inclined to think that this would yield elements in the first subcoset of 1 plus h, because remember when we add stuff in 2 plus h, 2 elements in 2 plus h, you get 4 plus h, but you can't do 4 because we're going mod 3 because h only has 3 cosets. So that would put you back in the first coset. But you look at the elements here on my edge labels, 7, 25, and 16, and notice that's actually in the second subcoset of 1 plus h. And so what happens is, I mean, we can look at this on the other side too. We can see there's this subcoset position shift that is what messed us up. If we didn't have that position shift, then we wouldn't have any problem here. But because of that position shift, it kind of screwed us up. And the reasoning behind this that we found out, so I'm going to kind of do a little side work down here. If you think about doing something from the first subcoset plus the 0th subcoset of 2 plus h, then what we get is we get something like something from 2 plus h in a sense plus 2 plus h. This is kind of scratch work. But if we write that down, that kind of looks like 4 plus h, but we can't do 4 because we only have 3 cosets. So it's really 4 mod 3 plus h. And so what we have to do is when we take that 4 and split it up, we get 1, but we can't just get rid of the 4. So we have this extra 3. And so that extra 3, when we move it into the subcoset kind of part of these elements as they're generated, it adds 1 more to that subcoset position. And so that's where we got messed up on this. So how did we take care of that? Well, it was a pain. So I'm going to go back to this and kind of describe what we did to take care of it. So first of all, we wanted to define a very clean way, if you will, to write how every element in Zmod str was generated. So remember, we're letting, so I'm going to write this down, we're letting H be the subgroup generated by T, and K is the subgroup generated by RT. Okay, so we let I here be between 0 and T minus 1, so that this I is representative of which coset we live in, so 0 through T minus 1. J is representative of which subcoset we live in. And then this K over here, which is between 0 and S minus 1, K is representative of what position, if we order our elements in order from each subcoset, what position that each of those elements lived in. So If we look at the ordered elements, S elements, in each subcoset, so each subcoset looks like JT plus K, and that's a subcoset of, say, I plus H. So we're saying we're in the ith coset, and we're ordering all those things from smallest to largest. Then we can write or calculate each element with this expression here. So it's the coset position plus, in parentheses, J times the K position. So remember, K is the position it's written in order of smallest to largest, starting from 0, times R, and then all times T. And we say that that's the element in the kth elemental position of the jth subcoset of the ith coset. So I know that sounds terrible. It's terribly confusing, but it works. I mean, we can write every element in this manner, and the nice thing about it is we can literally identify the exact position that each element is in terms of writing out our distinct subcosets for each coset. So here's kind of where the issue came in with this shift that we saw in the subcoset position. So if we add any two elements in the I plus H coset, then we know that that yields an element in the 2I mod T coset. Okay, well, if 2I mod T is just 2I, meaning that essentially the 2I value is not more than halfway across my coset locations, then I don't have any issue. I don't really have any issue with doing a subcoset shift. So when did that shift start happening? It started when we had to start taking mod of this 2 times I. So what that means is that the I value is either bigger than or equal to T plus 1 over 2 or less than or equal to T minus 1. So it's sort of more than halfway across my list of potential cosets. And so if we think about adding consecutive elements in the coset I plus H, then we know we get elements in this 2I mod T plus H coset, regardless of whether or not 2I is subject to mod T or not. It was just telling us which subcoset we were in that got confusing. It didn't match up if we actually had to take mod on mod T on 2I. So labeling the snowflake graph up into the point where 2I was not subject to mod T, meaning it's between 0 and less than T plus 1 over 2, we would be fine. So what we saw is a way to kind of quickly fix our initial attempt at labeling this snowflake graph by just labeling everything the way we had up until that point. So once we got our coset position being bigger than or equal to T plus 1 over 2, then we had to do something different. So what we did, and this is what my students, Holly and Walker, kind of noticed about this. They noticed that first set of branches, everything was good, and we got exactly what we wanted to when we didn't have to take mod on 2I. And then they're like, well, what if we just took a bunch of paths? And so we remove the other branches from the snowflake graph and just take a bunch of paths and connect the paths in a clever way to the root of the snowflake graph to get what we want. Because if we add consecutive elements in any coset I plus H, regardless of whether or not it's subject to 2I is subject to mod T or not, then we still get unique elements back. So what we did here is we had a theorem, or they kind of developed this theorem, where if you have your S, T, and R bigger than or equal to 1, the product is bigger than or equal to 3, and they're all odd, then the graph where we take T minus 1 paths of length S times R and union it, this is not a disjoint union, I should say, union it with this snowflake graph STR plus 1, then this is harmonious provided exactly one unique vertex from each of these paths is adjacent to the root of the snowflake graph. So I'm going to show you a terrible example. This is the example that they created. It looks horrible, but it actually works. So this is a harmonious labeling of the graph. So what we have here is this is SF 3, 5, 5 plus 1, and we're unioning that with a bunch of paths of length 15. So this is union with 4 paths, so which is 5 minus 1 of length 3 times 5. Okay. And so what we did is we basically just set up the snowflake the way we had. So proving this was a little bit more technical, but essentially if we're doing this here, I think we're working in like Z mod 135. It's kind of terribly big. But so I'm not going to go through this too much, but basically if I defined my subgroup H here, I would have to do it in a slightly different way than we did before, but we'd essentially have 9, I believe that's right. Yeah, 9 cosets of H. So I think H is generated by 9 in this case, so it's a little bit different. And so if I have an I, like if you think about this as being like our T before, it's not the same T. Then if I did T plus 1 over 2, right, then that's 5. So I get 5 branches on the snowflake graph, which when I add things from those coset positions, I don't have to worry about going mod T here. And then I have these 4 remaining paths, if you will, that that those would give me an elemental position shift, but since I'm labeling things in a path, I don't have to worry about it because everything sort of gets recovered. So don't spend too much time looking at that. This was just something that they put together. It was a really nice depiction of a sort of complicated example, which is why I wanted to show it. So that didn't really answer our question. We still wanted to know how to harmoniously label the snowflake graph by itself. So what we did is we switched things up, and this was sort of observed by accident, because what I did is I actually just started running computer simulations to find brute force harmonious labelings on a simpler snowflake graph, and it came up with a whole bunch of them, and the first one that I looked at happened to notice a pattern in it. So we let H be generated by R instead of T, keep K the same, and that gives us R cosets of H and T subcosets of K, each with S elements in each coset. And then so what we do here is we fix a subcoset for each branch of the snowflake graph, different from the coset. So fix a subcoset, and then we take the T branches and refer them as 0, 1, 2, T minus 1. So each of those branches is going to refer to a subcoset location, not a coset location like we thought before. And so we label each of the PR sub-branches on the jth branch with the ordered elements from the fixed elemental position K. So what we do is we kind of fix an elemental position on a particular sub-branch. So if we take the jth sub-branch moving away from the root, then we fix a certain elemental position on that way, depending on a certain ordering. So we do it in a certain ordering. So then we label elements from the I plus H coset with I even for one side of the central vertex of each sub-branch, ordered smallest to largest as we move away from the central vertex, and then pick elements from each I plus H with I odd for the other side of the central vertex of a sub-branch, ordered largest to smallest. So we have to switch the order. It's kind of a weird situation how we have to switch those orders. And then finally, if J is even, so remember J is the subcoset position, so that's our jth subbranch, then we label the subbranch so that the elemental position K is ordered largest to smallest, moving away from the root. And if J is odd, we do it so that we're moving largest to smallest, moving away from the root. Now, that being said, we could have switched those kind of like Dr. Roblee and Abueida did in their proof. So this is the example here where we actually have a harmonious labeling of this snowflake graph SF355 plus 1. I mean, I guess don't stare at this too long, but if you think about this, so we're working in Z mod 75, and this is kind of my last big example. Then my H here is going to be the subgroup generated by 5. So that's my 5. This is my R, by the way, and then my K is going to be the subgroup generated by 5 times 5, or 25. And so what you can see here, this first branch here, this corresponds with my 0th subcoset elements. And then what I do, is I actually start with the elemental position on each of the sub-branches. So these are elemental position locations moving away from the root. And then I flip that going from, so that's largest elemental position to smallest elemental position moving away from the root. And then on one side of the sub-branch, we have our odd coset elements. And then on the other side of the central vertex of each sub-branch, we have the even coset elements. Okay, and then we order the odd ones from largest to smallest moving away from the center, and then the even ones from smallest to largest moving away from the center. So we maintained this ordering for every branch moving around, but we just flip-flopped the elemental position ordering from, so if the elemental or the sub-branch, the subcoset was even, then the elemental position went from largest to smallest, and then if it was odd, we went from smallest to largest. So like down here, this would be our first subcoset position, which is why we started our smallest subcoset element would be 5, and we're moving away from, in terms of elemental position, from smallest to largest. So that's kind of the setup in a nutshell. I mean, proving this was a lot more technical. It required a lot of lemmas and stuff like that, and it was a pain. So this is our theorem, the graph SFSTR plus 1. So we did cases to show that even if we just assume that they're all bigger than or equal to 1, and this product is bigger than or equal to 3, we get an all odd, then we get that thing is harmonious. So that's our main theorem. So just real quick, finishing up. One example that we did look at, so this is an example where they're not odd, SF223 plus 1. I sort of found this harmonious labeling just by brute force calculation on the computer, and there's no pattern to it. This is just one of a bunch of them that I observed. So this kind of leads to a question of whether or not we can show somehow that other snowflake graphs or even other starlike trees are harmonious. Now, in terms of just permutations of labels, we had only like 1 out of 16,632 that were actually harmonious when we fixed the root at 0. So not very many of them in reality ended up being harmonious in that brute force calculation, but there were quite a few. So the obvious follow-up questions is whether or not we can determine if the starlike tree or the snowflake graph are harmonious in general. That means if we don't require that ST and R are all odd. But the big problem is if we do that, if we even have one value being even, then that means we're working in Z mod an even number. And so using the method of cosets and subcosets, all the properties we showed, that wouldn't be viable anymore. So that doesn't really help us. So I guess the question is, where do we go from there? Well, I don't really know. Maybe start looking at a different question, because I'm not really sure how to approach those other problems. But anyways, there's some of my references, and that's all I have.
Thank you so much. Do you have any questions for our speaker? Maybe I would ask Dr. Roblee this topic.
Yeah, he's the one that suggested this to me, so you can thank him partially for this mess.
Yeah. So.
Yeah. Well, first of all, sorry for being late. I lost track of time, but it was a really nice presentation, and they're really nice results, and those are really nice symmetrical graphs. So, um, being a Libra myself, I like balance, and and those graphs have a lot of balance to them. And
They were all done in GeoGebra and using a bunch of just trigonometry and angles and unit circle stuff to get the vertices all symmetrical.
oh wow, that's impressive. So yeah, they're beautiful graphs, and and really, I think it was a really nice idea to use the idea of subcosets, and that's one thing that really stood out to me, and one thing that my co-author and I, Atif Abueida, that we were missing in our when we did the starlike trees, and so that really made that really expanded greatly the type of graphs that you could consider to harmoniously label, and that made the difference. And so that's um, that that was impressive, and it was even more so because you worked on it with students, and they were able to help figure out a lot of this too. So that's kudos to y'all for that. And the but yeah, we need to get together here soon to where we can maybe try to figure out maybe a new direction, or a new problem or problems to work on, because that seems very promising, and maybe some new classes of graphs to extend those ideas to. And but one thing that we've worked on recently, that Atif and I worked on in probably April and May, is we tried to extend the idea of, if everybody notices, in the you can recycle one of the vertex labels when you're dealing with a tree, but just by because there aren't enough labels to go around for all the vertices the way it works. So you're allowed to use one label twice. So we're so one idea that we've considered is, what if you had like a forest, which is when you have disconnected trees and all, how would you define harmonious labeling then? So we
Yeah,
we were thinking maybe to allow, like, if you had just a disjoint union of two trees, to allow maybe two repeated labels, but could you use the same one to repeat, or do you have to use a different one for the extra repeated one? So we came up with some sub definitions and all too. So
I'd be
that's
interested to see that, because I that's something I think I had asked you a while back when we
right.
were kind of finishing this, and because I wasn't sure if there was already I mean, because some of this graph theory stuff in terms of the harmonious labeling, it was new to me until you suggested it. And so one of the questions that I had when you told me that when you have a tree, you get to recycle a vertex, I was like, well, what if you start unioning a bunch of trees? And then can you recycle? So we looked at actually a couple examples like that. We just didn't really go anywhere with it because we didn't have time. But that was something that I had thought about too. So I'd be curious to see what you guys defined.
Yeah, I'll send that on to you. We wrote up a paper, and we had two different notions of it. One where you were allowed to use a single vertex after you've used up all vertices, um, so it's at least an onto function, the labeling, but you're beyond that, you can use any single label as many times as you want to after you've used them all up. So we
Right.
called that harmonious, and because other people had asked that same question too, and it seemed to keep coming up. So we figured we would ask some people around what they knew, like Gally, and I asked Gally, and he had never heard of that.
Yeah.
I'm trying to label forest, and he's the guru of labeling, so he didn't know. So we just kind of went with a couple different ideas, and so we defined what a just a general harmonious labeling will be, where you could use a single label so much if you wanted to, as long as you've used all of the others. But then we thought, well, that maybe that wouldn't satisfy people that like balance. So we tried to come up with one that was called an equitably harmonious labeling too, where where you use them as much, you spread them out as much as possible once they're all used. And in other words, yeah. So I'll send that on, and if anybody else wants me to that, I can too. We sent that off to a conference proceedings at from the Boca Graph Theory Conference. But if anybody else wants to look at that, we can.
Yeah, because we had looked at just with the starlike trees, like if you have something like this and just a regular starlike tree, because one of the, that corollary I said to y'all's result, something like that would be harmonious. And then if you union it with another copy of it, then you would get kind of another harmonious thing. You just have to I mean, it's sort of almost trivial if you recycle the root again, like you did before. So if you just keep recycling that root, but I mean, sure, there's other ways you can do it too, but that was one of the things that we looked at. We just, like I said, didn't know how to define it at the time.
Okay, so I think I saw that Dr. Voloshin would like to talk a little bit about this talk.
I liked the talk very much. It was wonderful. Thank you. Nice pictures, good meaning, and very meaningful and serious proofs and serious mathematics, because this problem in general is very difficult. So you see here, that's how difficult it is just for trees and and this combination. So for general graph, it will be even more difficult.
Yeah, in our paper, in the write-up, it's a little bit more confusing though. So I tried to stay away from throwing in all of our group theory lemmas and theorems that we actually use here, because it would have just been, I mean, even my eyes kind of glaze over when I look back over those a little bit, because it's just so many different parts to them and very long proofs. I mean, we spent more time just proving how adding up elements from certain subcosets and cosets and elemental positions where they would actually land. We spent more time just proving that stuff than anything else, and then of course developing our sort of unique ordered sets to put in particular places on our graph. I mean, proving how those added up and what sets those yielded. I think that's where we spent most of the work. So there's more work in the group theory proofs in the paper than there is in just proving that the graphs, those two main graphs, the snowflake graph with the paths and the one without the paths, are actually harmonious. So yeah, it was definitely a lot to keep track of. I actually had somebody ask me when I was talking to them about this, I was like, so are you going to look at doing subcosets of subcosets now? And I said, no way.
Okay.
Anyway, you were very successful in this very good presentation, even for the people who do not understand at all. The pictures were very nice, drawings very nice, so therefore it was beautiful. Thank you very much.
Oh, thank you for saying that. I appreciate it.
Yeah. So I think some of you might have some questions, but the talk lasts already more than 1 hour. So if we have
sorry about
questions,
that.
Yeah. So, no, it's fine. I mean, I just want to mention that if the audience has questions, so they can send directly to you. And I think we can stop the talk right here. Thank you very much again, Jared.
Yeah, thanks for inviting me.
Thank you.
Thanks
Thank you.
for interesting talk. Yeah, thank you.
Thank you.
It's funny hearing the clapping. I was thinking last time I missed last week's talk because I was at a different time and I had a previous thing, but the one before that I just remember thinking we need to have a little wave file at the end of this to just hear like a big audience clapping and just play that for this week.
Okay. Yeah, I will send out another announcement about the next talk. Okay. Thank you.
And
okay,
thank you for organizing this. This is really nice to actually have some medium and outlet to present work again. So I think you guys deserve a thanks too for putting this together. So we appreciate it.
Yeah. Thank you for joining us.
Okay.
Okay.